Okay, let's get chapter 4 covered. I've given you a new handout for today. And I want you to also grab your binomial formula. It's in your guided notes book. Make sure you know where that is, and we'll go over a little bit of stuff to make sure you know how to use it today. And let's take a look at your formula sheet too while we're doing this, because these are the two things that will be provided on your test for you, okay? Formula sheet, we're into chapter 4 now, so it's on the second page. By golly, we've already made it to the second page of our formula sheet. Look at us. So these are the only formulas that are in chapter 4. Not many, and they're not very complicated. They're pretty easy. And you can do a lot of this with your calculator. So I'm going to try and go over a few of those today. I think I did some examples of calculator in your video. I do more examples of using the formulas and going through the formulas in the videos, and try to cover the calculator stuff in class if I can. So let's just talk about a few problems. Now, I'm not going to work through every one of these. Some of them I'm just using to point out certain things to you that might be confusing, okay? The first one here says that it has a binomial probability, I'm sorry, not a binomial, a probability distribution. It's a discrete random variable. Look, the random variable is numeric and whole numbers. It's a discrete random variable is what it is, okay? So it's a discrete random variable for the number of cheesecakes they sell in a bakery. And so X is the number of cheesecakes sold on a randomly selected day. And this is the probability that it would be that number. In other words, the probability that they would sell no cheesecakes is 0.3, that they would sell 5 is 0.24, 10, 0.14, they left a big blank there, and 20 is 0.12. And you're supposed to fill in the blank. Now, you know how to do this. You just think you might not think it through at first. But when you have a complete probability distribution, all the probabilities of every possibility that can happen, and these are the only possibilities that can happen, is 0, 5, 10, 15, and 20, equals the number what? If I add all of the probabilities together, what does it come up to? 1. So if I'm just missing one of them, that should be easy. I simply add the others and subtract it from the number 1, right? So I would add all of these together, and I would subtract it from the number 1. I would add these together, I'm going to get 0.8. When I subtract it from the number 1, that's the missing probability. All you have to know is that this has to sum to equal 1, okay? Now, if you're missing 2 of them, you can't do it. But missing 1, you can always find the missing probability. Now, let's just look at a few of these. What's the probability of selling 15 in a given day? Well, do you know how to read these things? The probability of 715 is 0.2, isn't it? And then, let's look at wording. At least 10, okay? At least 10 includes the probability of 10, doesn't it? Or it could be that it could be 15, or it could be 20 cheesecakes. In other words, it could be any of these 3, and it would be at least 10. So I'm going to add them together because or means add, right? And I'm not adding the numbers 10, 15, and 20. I'm adding the probabilities for 10, 15, and 20. The probability of 10 is 0.14, 15, 0.2, 20, 0.12. That doesn't look too bad, does it? When I add those together, and I'm doing a lot of math for you today because there's so much to cover, and I want you to get the concepts, but I would like it if you would go back and check the math. Make sure you can work it, okay? And that your calculator is doing what it should be doing, and that's why I'm giving you the correct answers here. So now, probability of selling 5 or 20. Now, when you see or, you should say, that's always an added probability, isn't it? When I say the probability of 5 or 20, I'm going to find the probability of 5 and add it to the probability of 20. That is that or situation, right? 5 or 20. Now, let's see the probability of selling 25 cheesecakes. Can you figure that one out for me? Does anybody see the option of selling 25 cheesecakes? That means it never happens, okay? So what's the probability of something that never happens? 0. So you can just say, well, that's not going to happen. the probability is saying, now this is another, I'm just trying to make sure you understand the wording. Do you understand what it means when it says at most 15? What does at most 15 include? I've got 1, 2, 3, 4, 5 different probabilities here. What's included in at most 15? 15 and below. So this one, 4 of them, right? Now listen, you can add those 4 together, couldn't you? Or there's a shortcut. What would you do? Yeah, take that one, which is 0.12, subtract it from the number 1, and it will be the rest of them, won't it? I can do that one in my head, I think. Isn't that right? 1 minus 0.12. I'll write it down in case you're wondering where I'm getting from later. Okay? Or you can add the 4 together. It's up to you how you do it, whatever you understand. But guys, if they give you 25 probabilities and they are only interested in the probability of 23 of them, wouldn't you just add the 2 that they're not interested in and subtract it from the number 1 rather than calculating all those other probabilities? Remember that magic number 1, they all have to add up to 1. So if you can use it in your favor, to your advantage, do it. Now, do you know what expected number means? They represent it, they say expected number of x. But when you see that, what you should think is that's the mean, okay? The expected value, the expected number is the mean. And you would find the mean of these cheesecakes by using this formula that we were talking about, where those formulas are. This is a discrete random variable, so here's the mean. It is x times the probability of x, and then you add those together. Now, real quick, are you using a graphing calculator or not? Yes? How many are using a graphing calculator? Let me see your hands. Okay? So, so that's going to be a given. Let me just, I think that's going to be pretty simple. I'm going to do this real quick without the calculator or with the non-graphing method, but then I won't do any more. I'll just use your graphing calculator, okay? If you need that help, go back to the videos that we already saw. If I want to calculate the mean, where did it say that? Why was I calculating mean? I'm going down here. I'm going to take this distribution, this discrete random variable x distribution. I'm going to calculate the mean, the variance, and the standard deviation, okay? Actually, guys, forgive me, I'm going to skip that one because I've got one just like it over here. Can we go to the next page and do that one instead? All right, here it is. Once again, it's given us a probability distribution. It's asked us to fill in the missing 1. So I would add everything else up, subtract it from the number 1, and I would find the missing blank here, which is 0.38, okay? Any questions on how to do that? Does that make sense to you? So now if I want the mean, what's my formula? Well, the mean is equal to the sum of x times the probability of x. It's an odd way to calculate mean, but it's a probability distribution, so it's done that way. So first thing you have to do is multiply these 2 columns together, and you get the x times the probability of x column. And then you add them, and that will be the mean, okay? So when I multiplied these 2 together, if you want to just follow along with me, I'm going to tell you what your answers would be. That would be 25 times 0.13, and then 26 times 0.15. Wait a minute, that's not it. Sorry. I'm giving you a wrong number here. Scratch that out, make it 3.25. So, okay, is that better? That one's 3.25. And this second one is going to be 3.9. And this one is going to be 4.86. This one will be 10.64. And then I would have 4.64. I would add those together so that I had the sum of x times the probability of x. And when I added them together, I got 27.29. And that is the mean, or the expected value, right? Everybody clear on those calculations? It's not hard. Okay, so now the next thing they're asking is for this, the standard deviation. Well, now that's A harder formula, this is what it looks like. And here's a caution I'm going to give you. If you're not using a graphing calculator and you're doing this with the formula, then that negative has nothing to do with that exponent. You're not squaring a negative number. You're squaring a number and then sticking a negative in front of it. You understand the difference in that? Is that shaky for you some? In other words, it's like this. If I have negative 8 squared, then what I really have is negative 8 times 8, which is a negative 64, right? If I have negative 8 squared, I have negative 8 times negative 8, which is positive 64. Got it? The negative, if it's just stuck out front, has nothing to do with the exponent. Exponent does not touch it. So you should keep it in mind. So we're going to look at this standard deviation with the formula. It says to take the square root of the negative mean squared and add to that the sum of x squared times the probability of x. Well, we didn't do x squared times the probability of x, but you are veterans of this and you know how to do it. I would just come over here and say, I got x times the probability of x, don't I? I'd make another column. And all I have to do to turn this column into that column is multiply it by x one more time, right? X times the probability of x. I already multiplied x times the probability of x. So if I multiply it times x, if I take these numbers and multiply times x, I'll have x squared times the probability of x, right? You good with that? So when I do that, I come up with these numbers I was trying to give you a minute ago, 81.25 and 101.4 and 131.22, 297.92, 134.56, and when I sum them, I get 746.35, and that would be the sum of x squared times the probability of x. That's what that's equal to, okay? So here I can fill in this. I can say this is equal to the square root of negative 27.29 squared plus 746.35, and I need the square root of that. That's the standard deviation, okay? Now look, that's not hard to do in this calculator if you have a calculator that does square roots. Oops, sorry. Okay, so I'm going to take the radical, and under it I'm going to say negative, which is not the same as your minus sign, right? You guys understand how that works. I got 27.29, and I'm going to square it. And then I'm going to add to that 746.35, and I'm going to just take that one. There it is. 1.267, decimal places is probably all it told me to go to. I'm good with that. So this is equal to 1.267. Now, what if they ask, that's a standard deviation. That's our symbol for standard deviation. But what if they ask you for the variance, right? Well, the variance is this number squared. Or it's everything under here without being under the radical sign. Now, if you take this number, listen to me, if you take this number and you square it, you can be off by some thousandths of a point. Just be aware of that, okay? Because it's more precise to actually take this and type it in like that. I say negative 27.29 squared plus 746.35, okay? 1.6059. Whereas if I take 1.267 and I square it, well, I'm not off too much, am I? A little bit. You see it? You will be off a little, though. But it's the same basic premise, however you get to it. All right, take a look at this now. Let's go to the calculator and see if we can do this with the calculator. I don't think we talked too much about this, but you do know how to enter things into your calculator as a list. I'm going to go to my calculator, and I'm going to clear a couple lists, list 1 and list 2. Okay, because I'm going to always work in list 1 and list 2 because it makes things easier for me. And I'm going to put in list 1 and I'll put it here for you so you can see it. I'm going to put these in list 1 and these in list 2. Okay, so I'm going to put the X values. I got 25, 26, 27, 28, and 29. Those are my list 1 X values. And then I'm going to put down the probability of X. 0.13, 0.15, 0.18, 0.38, 0.16. Okay, now I'm going to go and do the same thing I've been doing. I'm going to go stat, calc, one variable statistics. List 1 is my list. List 2 is my frequency list, and I have to use both of them. So you may have to enter parentheses L1 comma L2 when you're doing this, okay, if you don't have this menu. But look what it gave me. The mean, 27.29, right? The standard deviation, it only gave me one of them because it says my sample size is a 1. You know why? It took this as the frequency list, and when it added up all of those, it came up with the number 1, right? So it says your sample size is 1, so it didn't give me, it says you don't really have a sample, so I'm just going to treat this like population data, and I come up with this standard deviation. If you wanted the variance, you'd have to square that number. Any questions? You can use the calculator to do these if you treat the X values as your X values, and if you treat your probabilities as your frequencies, okay? And it'll still do it under one variable statistics. Are you good? Okay. All right, let's go on then. I want to make sure in this next part, I just want to make sure you understand how to interpret more than anything for this number 4. I've got a distribution. It's a discrete random variable. It goes from 0 to 5, and these are the probabilities. If I summed those probabilities, I would come up with the number 1, of course. And it's asking for certain probabilities. Now, what I want is the probability that X is going to equal a certain number. Well, that's just going to be one probability, isn't it? I can pick it out of the list, out of the table. But what if they ask me for the probability that X is less than 2? You got to tell me, what's included in X is less than 2? Well, yeah, it's the probability of 0 or 1, right? Now I'm saying or because it could be either one of them and it would still fit the criteria, right? Less than 2. When I see or, I know I have to add. So I'm going to take 0.322 and I'm going to add 0.237. I don't use 2 because it said it had to be less than 2. And I'm going to come up with 0.559. What about this next one? Greater than or equal to 2. What does that include? Yep, 2 or 3 or 4 or 5. Or 1 minus the probability of 0 or 1. Do you understand what I'm saying to you? You can add up these 4 numbers, or you can add these 2 up and subtract them from the number 1, and you will get the same thing. Does that make sense? Sometimes when you get long probability lists, it makes sense to do that. I'm going to let you try that on your own later. I'm just going to tell you what that answer is. It's going to be 0.441, okay? What about this one? X has to be between 2 and 5, but it includes the 2. Does it include the 5? You understand how to read it, right? So the probabilities that we're interested in, 2 or 3 or 4. Okay? Sometimes it's the hardest. This is our hardest task, is interpreting which probabilities they're asking us for. So make sure you understand the terminology. The Boolean operators, okay? The inequality operators, those are really important for you. This one comes out to be 0.39. I'll let you check it later. And then it asks a question about the shape of this distribution. Well, now the shape of it is either going to be symmetric or skewed left or skewed right. True? Now some of you on the last test missed that skew question. The skew is where the tail is, the little skinny tail. That's where the skew is, okay? So take this chart And instead of drawing a chart, just turn it sideways. And say, okay, this is 0.3, this is 0.3, 0.2, 0.1, 0.1, 0.0, right? Isn't it going down? Don't I have a curve that looks like this, you know? Wouldn't I have a curve that looks something like that? Where's the tail of that thing, left or right? Yeah, this is a right skew. So when they ask you the shape of it, just take the chart that they've given you and see if you can figure it out from that shape, okay? Draw it. It would be where's the tail is what they're asking. Okay, I don't know if any of you have tried homework problems in Chapter 4 yet, but I'm really hitting things that I think would confuse you, okay? And that's all I'm trying to do here is hit the stuff that might confuse you. If you have not seen the videos of the lecture for Chapter 4, I expect you are lost right now, and you probably should be lost right now. So that would come first. If you have not watched those videos, I don't know if there's 1 or 2 of them out there for Chapter 4, but watch Chapter 4 videos, then go in there and see if this makes more sense. You might need to watch it again. All right, this table talks about the frequency of nest size. In other words, it's the number of eggs. It's the number of eggs that they found in 100 blue heron nests, great blue heron nest, when they surveyed Indian River County. Now, I created that number. This is not exactly accurate information because I made some numbers up here because I wanted our math to be easy today. So I said, okay, 100 nests, out of 100 nests surveyed, they found, in 11 of them, they found 0 eggs, and in 15, they found 1 egg. You see how it's read, right? In 39 of them, they found 5 eggs. They didn't find more than 5 in any of them, right? And of course, they didn't find a negative number of eggs, so that was the total distribution, right? And so they want us to come up with probabilities. What's the probability that you would go and survey one of those nests and there wouldn't be any eggs at all in it? What's the probability? Well, there were 11 found like that out of how many, guys? 100. So the probability is 11 out of the total frequency of 100. Well, I did this on purpose so your math was easy. You just have to move the decimal, right? Finish that chart real quick. Give me the rest of those probabilities real fast. And then when you finish, just glance up here. I'll have them written for you. Okay? Not really necessary when it's dividing by 100 to be, you could just move the decimal. But please be aware of this. After I created it and I gave you that easy math to do, I thought, well, somebody out there is going to think, okay, you always just move the decimal 2 places. Well, you don't. It's only being done that way because the frequency, total frequencies, happen to be 100. If the total frequencies had happened to be 122, you'd have to divide each of those by 122, okay? So understand that's just happened that way. All right, and let's take another look at this. We have an experiment. This one, I'm just going to tell you right up front. I went to some elaborate measures to explain it because it seems to be a sticking point for so many students. But do you remember drawing the tree diagram in the last chapter? Okay, we're going to go back to the tree diagram with this one. Okay, it says that there was an experiment where they tossed a coin, a fair coin, which means that it, wasn't weighted, a fair coin, and they tossed it 3 times, and then they count the number of heads. And we're going to address these questions. First, they want to what's the random variable? What are we looking for? Well, what did they count? The number of heads, right? That's the variable, number of heads in 3 tosses, however you want to word it. Number of heads in 3 tosses. That's my variable. So what are the possibilities? Well, if they tossed it 3 times, you should have 4 possibilities because 0 is always a possibility, right? And there could be a 1, there could be a 2, there could be a 3. That's how many heads could have occurred. Could have 0 heads, 1 head, 2 heads, or 3 heads. Now, you know the probability for heads is equal to what? Yeah, that's an easy one, right? Okay, so just for this sake, what's the probability of tails? Yeah, so keep that in mind, right? This just happens. These two probabilities are exactly the same. Now, I drew this out for you because I didn't want you to have to draw it, and I wanted to be able to illustrate it. And this is my chart, my tree diagram chart of tossing the coin 3 times. Now, and like I said, this is on the video, so you can get this picture later if you want to. But just listen to me, or you can take a picture later if you want to. Listen to me. This represents the first toss of the coin. It's either heads or tails. And then the second toss, well, based on the first toss, it was either heads or tails, and this one was either heads or tails too. And then we get deeper, this tree gets bigger as we go to the third toss. But each time I toss it, I have the same possibilities. It's either heads or tails, right? And then I got to say, okay, this scenario is 3 tosses, 3 heads, right? Okay, what are the probabilities for 3 heads? Well, it's 0.5 for each time. So this is saying heads and heads and heads, right? Isn't that? So when you have and, don't you multiply probabilities? So I say 0.5 times 0.5 times 0.5, and I come up with that probability of 3 heads is 0.125. Now that makes sense, doesn't it? But when I go through each of these scenarios, do you see any of the combinations that is not going to have a probability of 0.125? I mean, think about it. Heads, heads, tails. What's the probability of tails? 0.5. This scenario, 0.5 times 0.5 times 0.5, 0.125. What about this one? Heads, tails would be 0.5. Heads would be 0.5. 0.5 times 0.5 times 0.5. I mean, isn't it all 0.125? I mean, couldn't I just say, yep, they're all going to be 0.125? Are you good with that? You see what I'm saying? Okay, so what question are they going to ask us that's not going to have the same probability? Or are they going to ask for combinations of those? Well, when you ask for combinations, you got to add the probabilities together, don't you? This or that. So what's the first question I have to answer? I can't find my paper. Hang on. Okay, first question I want is, what's the probability of 0 heads? The probability of 0. Can you find a scenario up here that represents no heads?
Yeah, tails.
This one. This, I would say, is 0 heads. I'm just going to put it in a little block. That meets the 0. Does anything else have 0 heads? Okay. Probability of 0 heads, then, is 0.125 because it only includes that one, doesn't it? Okay, so that one we're good with. Okay, 0.125. Now, what's the probability of 1 head? And we got to do the same thing. Okay, do you see any that have 1 head?
So the double tails.
This one? I'm going to just put a 1 here, okay?
Then you have the THT.
This one?
Yeah. And then the one below it.
So there are 3 of those, right? So I could say 0.125 plus 0.125 plus 0.125, or I could just multiply it times 3, couldn't I? So I got 0.125 times 3, and I'll just tell you what that comes out to be. It is 0.375. And I'll come over here and write it down, just in case you wonder. It's 0.125 times 3, because there were 3 of those. Okay, what about 2 heads? All right, we're looking for 2 heads.
So the second one.
The second one. There's a 2.
And then
There's a 2.
and then the one.
And there's a 2. How many of them do we see? Because I'm running out of them, right?
Yeah.
So there's another 3. Going to be the same probability, isn't it? This is another 0.375. What about 3 heads?
Just one going on top.
So there's the probability. It's a 0.125. Now add these probabilities together, which I would do if I was doing this, and I should come up with the number 1, right? But that's my distribution, my probability distribution based on chance. Now, what's the shape of this probability distribution? Well, turn it sideways. Small on each end and bigger in the middle. Doesn't that look kind of like this? What would you call that shape?
Symmetric.
Symmetric. So this is a symmetric probability distribution. And then it says, what's the mean for it? Well, you know how to calculate the mean, or you know how to do the calculator to do it. Go into putting this in list 1 and this in list 2 and doing one variable statistics. So when you come up to the mean of this one, I'm going to tell you what it is. The mean is, you could do sum of x times the probability of x. But what you get with this mean is 1.5. All right? 1.5. Now, what I want you to do is interpret that mean for me. What exactly does the mean mean? It is the average. But it's the average of what? It's the average of what? I mean, say it to me in words. I'm tossing a coin multiple times. What can I expect to happen? For every 3 tosses, I would expect 1.5 heads, right? Every time I toss it 3 times, if I do it a lot of times, I would expect that expected value, that mean of 1.5 heads. Doesn't that make sense? Because that's half of 3, isn't it? I mean, you can't really use that all the time, but that's really what makes sense to me. So that's what the mean represents. You have to go back to the problem and say, well, if you do this experiment over and over, the mean is telling me that every 3 tosses, I'm going to get 1.5 heads. Does that make sense? Okay? So that's really important for this next test, is you can interpret these things, okay? I had students on the last test who said, you know, I really just got thrown. I got thrown because I was so confused about the wording. I knew how to work the problems, but I didn't know how to apply it to the statements that were said. And a lot of that is interpretation. You've got to know, you can calculate this all day long, but if you don't know what it means, it doesn't matter, right? I mean, if you don't know what the calculation stands for, it's useless to you. That's what the mean is, and that's why it's called the expected value. Okay, I'm going to skip over the next part because you don't need me for that part probably. Let's go over to the next one that I thought I needed some help. And let's talk about doing the same sort of problem, but this time we're talking about drawing cards out of a deck. So the probabilities for this one are not all the same. They're not all 0.5. We've got 52 cards in a deck of cards, and it's saying we're counting the number of aces. Well, I don't know if you know about cards, but there's 4 aces in every deck, right? So I got 4 of those out of 52, and they did tell us we're going to do this with replacement. So we don't have to worry about the fact that, you know, I drew it out and now I don't have so many cards or I don't have so many aces. You don't have to worry about that. They're putting it right back in, so you're starting over each time you draw. So they want to do 3 cards, right? There's the next thing that we need. We drew 3 cards. What are the possibilities of aces? Well, it could be 0, 1, 2, or 3, right? Those are the possibilities. And then they want to know the probability for each of those possibilities. So what is the probability of 0 aces? Okay, you drew 3 cards. They want the probability that the first one is not an ace, and the second one is not an ace, and the third one is not an ace. I'm going to use N for not an ace and A for ace, okay? So I want the probability that all 3 of them are not. Well, look at these numbers. You know that you have 4 aces for every 52 cards, right?
Yep.
Cards. That's the probability of it being an ace, isn't it?
Yep.
Well, how many not aces do you have for every 52 cards? How many are not aces?
48.
Exactly. You understand? So this is the probability that it would be an ace, and just embrace the fractions. Don't go immediately to decimals because it's too hard. So I got 4 out of 52 that are aces, and I got 48 out of 52 that are not aces. And I don't have to worry about replacement, so I can use these numbers all the time. So the probability the first one would not be an ace is going to be 48 out of 52. And says multiply, doesn't it? Second one, not an ace. Well, that's going to be 48 out of 52. And third one, not an ace, 48 out of 52. Now, you know how to do this. When you're multiplying fractions, you multiply numerators all the way across, and then you multiply denominators all the way across, and then you do the division, okay? When you do that, in the interest of time, I'm just going to tell you it's 0.7865. Make sure you know how your calculator is doing things, okay? Okay, that's the probability of no aces. What's the probability of one ace? Now remember, when I say that, remember the scenario with the coin toss. The order that they happen matters, so there might be multiple opportunities here for one ace to appear in 3 selections. The first one I choose could be an ace, or the second one, or the third one, right? And that's the only way one can happen. So there's going to be 3 of these. But what's the probability? Well, let's say that the first one is an ace, and the second one is not an ace, and the third one is not an ace. Well, the first one being an ace, the probability for that is 4 out of 52, isn't it? Second one, not an ace, would be 48 over 52. And the same for the third one, not being an ace. Now, I come up with that probability. I didn't do this one, sorry. I come up with that probability by saying 4 times 48 times 48, and then I said divided by, and I put this in parentheses, 52 times 52 times 52. That works for me, okay? And that, I gave it just enough order of operations to make it help, but I guess what I should have done, scratch this, okay? Let's do 4 times 48 times 48. That's my numerator, divided by 52 times 52 times 52. Better? I know it's going to do the multiplication before it does the division this way. If you don't do that, it won't do all multiplication and then all division. It'll multiply 4 times 48 times 48, and then it'll divide by 52, and then it'll multiply that times, it'll go straight around. So you have to use parentheses, okay? So I wanted to do this, and I come up with this number, right? 0.0655. But I have to think, are there more than one ways that this can happen? I could have ace, not ace, not ace, or I could have, and we'll put that one here, ace, not ace, not ace, or I could have not ace, ace, not ace, right? Or I could have not, and ace. There's 3 different ways that that one selection can happen, right? What do? I multiplied this times 3, because there's 3 possibilities, and I would take the probability and add them together, just like I did with the coin toss. So when I say 0.0655 times 3, I'm going to end up with 0.1966, or very, very close to that. Okay? All right. Now let's talk about the probability of it being 2 aces. So I'm going to say the probability of ace and not ace. And I know that there's going to be more than that scenario, but I'll get the probability for one of them, and it'll be the same for every one, right? So ace probability is 4 over 52. Second time, I would still have the 4 over 52. Third time, not an ace, 48 over 52. And I would multiply those together to get the probability that that scenario would happen, right? So once again, I'm going to put this in parentheses. I'm going to say this time it's 4 times 48 divided by 52 times 52 times 52. And, of course, I did it wrong. Oh, give me a minute. 4 times 48 divided by parentheses 52 times 52 times 52. I think that must be right. Okay, so I come up with 0.00, what is it? 5, and I'll call 5, okay? Now, how many different scenarios can you think of that would be this 2, okay? I'm going to come down here and say, okay, this one could occur. It could be ace, ace, and not ace, right? It could be ace, not ace, and ace. It could be ace, no, it could be not ace, ace, and ace. I'm just moving the N around, right? Those are the only three. So this one's going to also be multiplied times 3. So when I say my answer here times 3, I get this. 0.016, and I'll call it 4. Okay? And that's going to be that probability. What about the 3 aces? Ace and ace and ace. Right? 4 over 52 times 4 over 52 times 4 over 52. Okay, so let's see what that turns out to be. 4 times 4 times 4 divided by 52. Whoops, there I did it again. 52 times 52 times 52, close parentheses. And there, do you know how to read that? What is that? It says take this exponent, or take the decimal and go in a negative direction 4 places. Well, that means I'm going to have 0.000, and then I would have a 4, but I'm rounding to the 4th decimal place, so I'm going to round it to a 5. Okay? Good? Yeah. It says take the decimal and move it in a negative direction 4 places. So when I do that, I had this number, 4.5516. I took it and I went 4 places, didn't I? So I had to add 3 zeros. That's where my decimal is going to go. And then I want to round to this one, so I made it 0.0005. Okay, are there any other scenarios that this can happen? Any other ways you can have 3 aces? So that one is the probability, because there's only one possibility. Okay. Aren't you glad it's on a video that you can listen to again? Multiple times. All right. Now, you can get the mean of this very simply. You would take x times the probability of x, sum those up. That would give you your mean, wouldn't it? And you could answer any question about this now that you've created the probability distribution. All right, I want to talk to you about this lottery game. It's called a pick 4. And what happens is a player pays $1 and picks a 4-digit number. And if the numbers come up in the order that you picked them, then you win $3,400. Okay, so you've got 4 numbers, right? And you're guessing at all 4 of these numbers, and each of the numbers has to be correct for it to be right, for you to win. So what they say is write a probability distribution for a player's winnings. Well, there's only 2 scenarios. You're going to win or you're going to lose. And they want how much money will each of those equate to. Those are your winnings. Now, understand, you can lose, right? So your winnings would be a negative amount. So if you win, well, let's say if you lose. Let's take if you lose first. What are you going to lose?
$1.
Yeah. So we're going to say that's our first scenario. We lost. We lost $1. If you win, what are you going to win? Except you spent $1, didn't you?
So $3.90.
Yeah. So you got to subtract that $1. You got to say $3,400 minus the $1 that I. Yeah. So I got $3,399. That's what I would win. Okay? You understand? That's the only 2 scenarios, right? So what's the probability that I would win this thing? Let's do that one first, okay? Because then I can just subtract it from 1 to get the other one, since there's only 2 probabilities. What's the probability that I would win? It means that I have to get each digit correct, and it's a 1-digit number I'm talking about. So what's the probability that I guess, if I told you to guess a number, a 1-digit number, 0 through 9, how many possibilities is that? 10. Do you understand? It's not 9 because 0 has to be included. So I got a 1 out of 10 chance, don't I, of getting the first number correct. And then I've got a 1 out of 10 chance of getting the second number correct. And then I have to get the third number correct, and I have to get the fourth number correct. You see how I'm adding? You have to get the first right, second right, and. What do you do with these? Because it's and. They're not going to let you, if I said, it's not going to be or, because they're not going to let you win if you get some of the numbers right. You got to get them all right. Yeah.
So why is it out of 10?
Why did what?
Why is it out of 10?
Because you've got a possible, one-digit number has a possibility from 0 to 9. 0 to 9 is 10 digits, is 10 different numbers, right? The 0 always throws us because we forget. We say, okay, it's 9 numbers, but you forgot 0. Okay? Don't forget 0. Okay, so when I do this, I end up with 1 over 1 with 4 zeros, right? 1 out of 10,000. That's my probability of getting this correct. If you do this and you want to look at it like a calculator, with a calculator, what's my possibility? It just gives it to me in exponential notation. It's going to be 0.0001. Okay, take that and subtract it from the number 1 to get your probability of losing. Okay? If I say 1 minus 0.0001, I get 0.9999, don't I? Okay, well, you knew it's not, they were not going to make it easy on you, right? This is the lottery. So, possibility, probability of winning is here. Probability of losing is here. But what exactly is that telling us? Well, what's your expected value? In other words, if I play the game a bunch of times, what can I expect to win over a long period of time? That would be the mean, the expected value. How do I get it? Well, I say x times the probability of x, and I sum them, right? Well, let's do that real quick. Negative 1 times 0.9999 would be negative 0.9999. And then I'm going to add to that 33.99 times 0.0001. Well, all I have to do is move it 4 places, decimal 4 places to the left, right? 0.3399. Is that right? When I add those together, now I know I can do this one in my head, but I've done it before. You would use your calculator, make sure you were right. What is that telling me? In other words, how would you interpret that?
You still have a negative chance of losing.
You do have a greater chance of losing. You don't have much of a chance of winning. You got 4 numbers you have to pick correct, and the odds are definitely against you, right? But what is that expected value, the mean? What is it telling us? Every time you play the game, you can expect to lose 66 cents. That's what you can expect, okay? Yeah, but that shouldn't come as a surprise to us. How do casinos and lotteries stay in business, right? I mean, this is what? The majority of people are losing the money, and that's why. But you can calculate exactly what your expected value is, right? Okay, that's your correct interpretation. If you play it a lot of times, you could expect to basically have a gain of negative 66 cents per game. Okay. Next. All right, I just want to cover this because this little point here, I don't want to work this problem. I just want to point something out to you. When it says that 6% of Americans believe chocolate milk comes from brown cows, it just makes me sad. You guys know that chocolate milk doesn't come from brown cows, right? Okay, but this is a true statement. Okay, so X is a binomial, random variable. I mean, they asked a bunch of people and they surveyed their answers and they either said yes or no to the question, binomial. And what they said is they surveyed a sample of 15 people. What are the possible values? In other words, what could have possibly happened? How many of them could have said yes to this, okay? Well, none of them could have said yes, all the way to 15, right? What are the expected, what are the possible values X can assume from 0 all the way to 15? The reason I'm putting that up there is when you're creating a distribution, you have to remember that 0 is there, guys, okay? If I say I'm selecting 15, a sample of 15, you have 16 possible values because we have to include 0. If I told you I had a sample size of 99, well, there's 100 possible answers because I have to include 0, right? So you always got to add 1 to that. So that's the possible values here. And that's all I wanted to say on that one. Now let's take a look at this one because we just want one look at your binomial table and how to use it here real quick. This one says airline flights are on time 70% of the time. And anytime I see this in a binomial problem, I like it because my table has 70% as one of its probabilities. So the table looks like this. Sample size is the first column. Number of lost every word that was in my head, so give me a second. The values that I'm interested in being correct or interested in being a success is the X's, right? And then the probabilities that are in this table are listed across the top. Those are the p-values. So I have n, x, and p, and if I had an n value of 3, I would have 4 possible x values, just what we said, right? And I would be able to see those values for any of these combinations. Somebody took a calculator and did all the calculations for us, and so we don't have to worry about it. This is the table. It goes all the way through, I think, an n of 25, maybe 20 or 25, and this will be given to you on the test. So you'll have this table. It's a real savings, time savings, not to have to calculate these by hand. You can do this with the calculator. With the table, if it matches one of these values. You understand? If they're asking about a probability that has a probability of 0.62, this will not work. But if it said 0.6, you could use the table. You understand what I'm saying? So let's just use it real quick. On this one, it says we've got airline flights 70% of the time are on time. That would be my p-value if that's what they're looking for, and it is. I'm just shortcutting it here. And then they select 8 flights randomly. So that's how many I'm selecting out of is n. And then they want to ask the probability of 2. Well, x here is equal to 2. I found the pieces that I need to use the table, didn't I? So I go to where n is equal to 8. It's down here. And I go over, you're going to have to trust me on this one because you can't see it. That's the column where p is equal to 70. And then I'm going to go down to where x, the second column there, is equal to 2. And I find the probability is 0.01. And that's it. Nice that they gave it to me. So this is going to be 0.01. And because this table is written in 4 decimals, I always have a tendency to write it down like that. Now, the other questions, you would just take and combine these. At most 2 flights, you know how to do that. X could be equal to what? Well, it could be 0 or 1 or 2. So you would find those 3 numbers. We still have the same p-value. We still have the same n value. And all we need is the 0, 1, and 2. It's really nice to have a sticky note when you're doing this, and I'll try to have some for your test, okay? So you can stick it on the table, and otherwise sometimes you get lost. You would just add those together, wouldn't you? Do you understand how you use this table? Any questions on the table? Yeah, it saves you a lot of time. Like I said, it'll be there on the test, okay? Now, let's do something else. I have a binomial down here in number 11, and it has promotional game pieces, and you can win food or prizes, and the probability of winning is 0.105. Well, it's not in my table, is it? I'm going to have to use the formula, or I'm going to have to use the calculator. Now, I went into detail on the formula in your video. You know the formula. It's listed in this formula sheet for you, if I can find the formula sheet for you. The binomial formula is right here. It would be a combination of n out of n things taken x at a time, and then it's the probability of a success raised to the power of x, probability of failure raised to the number of failures, and that's the formula that you would use if you're not using your calculator. But if you're using your calculator, it's the binomial probability distribution function under second distribution, right? I go second, and I go here, variables, and I go to that distribution button, and that's where I can find it. So let's find the pieces we need. We need n, we need p, and we need x, okay? So I'm going to say n is, in this case, 25 purchases. That's how many I had to choose from. And probability of success is 0.105. And this time they're asking for winning 3 prizes. So that's what I want to find. And here I'm going to do it with my calculator, all right? I'm going to go to second distribution and go all the way down to the second page of it, and I want this binomial probability distribution function. That binomial CDF is a cumulative, and I would not advise even using it because it confuses people about which way it goes. But the binomial PDF, when I say enter here, it comes up and it gives me options. It's probably going to give you parentheses, and then you have to enter this. You have to enter n, comma, p, comma, x. And understand that p is going to have a decimal in it, okay? So it's going to look like this. I'm going to enter, what do I have? I already got this one in there. 25 is my number of trials, that's n. P is 0.105, x is 3, and it says paste it. That's what yours would look like if you don't have that little menu thing. You would type it in like that. Now you see it has 25 comma. Where is the comma? Because that's always confusing to people. Look over the 7 key. That's your comma, okay? So, comma, no spaces, n, comma, p. And for p, that probability is always going to have a decimal. So you're going to say, because rarely you're going to have a probability of 100%, right? That would be a 1. So p, you're going to put decimal or point, and in this case it's 0.105. And then you got another comma, and then you say the x value, which is 3. And when I hit enter, it gives it to me. Okay? Easy, easy to do with the calculator. Any of you want to see the formula? I think I've done that enough on the video that you're probably okay. All right. So second distribution, n comma p comma x. Ask me if you have trouble with your calculator after this, and I'll see if I can help you. Let's go on to the next one. This next one says there's a study, and 12% of peanut M&Ms are brown, 12% are yellow, 29% are red, 16% are blue, 18% are orange, and 13% are green. And you're already overloaded with percentages, and you're wondering, what in the world, how am I going to use all these percentages in a calculation? You're not. They gave you a lot of trash in this problem. They gave you a lot of extra. So you pick what you need, and don't worry about all these other numbers. That'll happen a lot in your problems. So what it's asking is saying, let's see, I'm going to select 4. So that's my n, right? Out of a selection of 4, they want these probabilities calculated. And every probability is asking about brown. So that's the only P we need. That's the probability. What's the probability of brown? Well, 12%, 0.12. Okay? And the only reason I'm doing this for you is because you need to learn to get rid of everything else in that problem. These probabilities are of no use to us, right? And then you just say, this is for 2 to 4. Well, in this case, 2 of the 4, sorry, x is equal to 2. Calculate the probability. In this case, 3 or 4, x is equal to 3 or 4. Calculate the 2 probabilities and add them together. In this case, at most 3 would include 0 or 1 or 2 or 3, or you could do the calculation for 4 and subtract it from the number 1, right? Do you understand that? Because they all have to add up to 1. There's only 4 possibilities. And then we say the same thing for at least 3. X would be 3 or 4. There's only 2 there. You can't shortcut that one because you would have to do 0 or 1 or 2, right? Okay. Let's talk about a cumulative probability distribution now, okay? So we have a survey of 70, and says that 70% of IRSC students plan to go on vacation after graduation, and we're going to select 5 students at random and create a probability distribution. They went down here and they told us that this was 0 through 5 is the possibilities, and they want to know what the probabilities are. Well, what is P in this case? 70%. Oh, good. It's in the table, right? What is N? It's 5. And then X is 0, 1. Well, let's go to that. Let's go to the X value, the N value of 5. Let's go over here to the probability of, I'll put a piece of paper here so I can't see it. The probability of 70%. And there's the distribution right there, right? Whoops, sorry. You can see it now. So what are the numbers that I want? 0.0024, 0.0284, 0.1323, so on. I just copy those 5 numbers down, okay? This is why it's so nice to learn how to use the table, right? So I did that for us. And it looks like this. Now, what is the cumulative? This is the cumulative distribution. Well, it just takes each x value and it adds up the ones above it. For the first one, it's always just the same as the first one, right? And then it would take this category or this value for x or this probability for 0 and it would add that one to it. So it's going to be this plus this equals that. Got it? So I'm going to say 0.0024 plus 0.0284, and I'll get 0.0308. And then I'll take that and I'll add the next one, and I'll come up with this, which came out to be 0.1631. And then I'll take that and I'll add the next one, and I'll have it here, which came out to be 0.4718. And I'll take this and I'll add that one, and it comes out to be 0.8319, which I will take and add to this. Tell me, what number do I get?
9999.
Yeah, it should be, or 1. Let's just call it 1. It should be 1. It should be everything, right?
Right.
So now look, 2 of these numbers in a cumulative distribution you never have to do math with. The first one and the last one. This is always going to equal whatever the first one equaled to, and this was always going to equal 1, or really, really close to 1, okay? Cumulative just means added as we go. Are you good with that? Sort of. You look shell-shocked. Are you guys okay?
Yeah, I'm fine.
Okay. Let's go to the next thing. This one I just wanted to show you because it was confusing. It is a uniform distribution. It talks about times, commuting times. And what I want you to realize is that each of these commuting times has an equal probability of occurring because it's a uniform distribution. The probability of it being an 8-minute commuting time is the same as a 12-minute commuting time, is the same as a 14. I mean, they were all the same. That's very rare that we have a uniform occurrence, a uniform distribution, but this is one. So what we say is, what's the probability that Andrew waits for 8 minutes? Well, how many times do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 10. There's 11 of them. And only 1 out of the 11 is 8, right? So that would be how we would find it. Each of them are equal distribution, equal probabilities. What's the probability that Andrew waits between 10 and 14? Now, it won't be defined like that on a test, because what this really means is that x is going to be between 10 and 14, okay? And that's what it would look like, okay? So how many fit that criteria? How many different times? Well, 10, 11, 12, and 13, but 14 does not. You understand? It looks like 5 to me, too, and the first time I counted it, I went, that can't be right. But when you look at it this way, 14 is not included, okay? Don't worry, it'll be defined like this for you, so you don't have to figure out the wording here. Yeah?
It says between 10 and 14. How do you know that it doesn't include 14?
You would only know because of this. It has to be written for you like this.
Oh.
And it will be. Don't worry about that. Won't happen to you on a test, okay? Yeah, because it's very confusing that way. So I'm going to say 10, 11, 12, and 13. So there's going to be 4 of them, right? 4 out of 11. That would be that probability. Right? And that's how you would calculate those. Okay. Lots of different things for these. Know how to use your table, your binomial table, and know how to calculate. Oh, wait a second. There's one thing I didn't do that's so easy. I didn't do it. But let's go back and do it real quick. Oh, here, let's just do it up here on page, page 6, up here with the M&Ms, okay? On average, if you repeat this experiment with the M&Ms over and over again, selecting 4, on average, how many do you expect to be brown? Well, what they're saying is, what's the mean? Well, for a binomial, it's the easy calculation. The formula says n times p. You don't have to know anything but the sample size and the probability of a success. That's all you have to know. Yeah. What about the standard deviation? What's equally easy? These formulas are in your formula chart. I just want to stress to you how easy they are. Everybody always says, but they didn't give me enough information to get this, but it's n times p times q, and you have to take the square root of it. Now, okay, so here's the deal. We know n and p, right? Is 4, and that's 12. What's q? You remember? Q is equal to 1 minus p. So q is equal to 1 minus 0.12, which is 0.88, isn't it? And that's it. I think I did that one. It's going to come out to be 0.6499. That's the standard deviation. What if they ask you for the variance?
Then you square it.
You could square it, or you could just say n times p times q, couldn't you? I mean, because that would be the squared value. Yeah.
For the discrete random variable, when you find the standard deviation, what's the difference between the formula that's in the book and the one that's on the sheet?
Okay, you're talking about the book that's in My Open Math?
The study guide.
Oh, the study guide?
Yeah, because it's x squared, then p parentheses x minus the mean squared. And this one is negative, like the negative mean squared.
Actually won't change it a bit.
It won't change it at all?
Well, it shouldn't, because it's just changing the order of it. One of them's plus, one of them's minus, right? So it shouldn't change it a bit. But let me say this. Use your formula sheet, okay? Ignore that, okay? Because I had an old formula sheet that was from an old class that we taught using Wiley, and that was the way Wiley worded it. But as far as just switching it, if you've got a negative plus, or that same plus minus, it shouldn't change it at all. I'll check that. What page is that?
It's on page 4.
Of chapter 4?
Yeah.
Okay. Thank you, because I'll fix it. I mean, I'll fix it for the next generation. But guys, use your formula sheet, okay? Because that's what you're going to have on the test. Any other questions? Okay, I'll see you. When do I see you? Wednesday. Yeah. Oh, thank you. Everybody, you have discussion questions in there that are in Blackboard, and you have one for this second module. And if you will do that before the test next week, or at the test, I'll let you have till the day after the test.
Okay.
Go ahead and do the discussion questions, okay? They will count toward your attendance points. Thank you.